Hi everybody, it's Christina, your instructor. So just in case it snows tomorrow, I wanted to go over the PowerPoint, so end of the respiratory PowerPoint and the beginning of the digestion PowerPoint. Oops, let me go back here. So if we don't have class, I will ask you to watch these and follow along instead, as well as completing some activities. So let's get started. So last time we ended on gas exchange and transport, and I'm actually backing up a little bit because we did do partial pressure stuff already, but never hurts to review. So the learning outcomes are: define partial pressure. So what does that mean, and how does it affect diffusion of gases across the respiratory membrane? Remember, this is the interface between the blood and the active tissues, or the interface between the blood and the alveolar air. We will describe gas exchange in the lungs and in the systemic capillaries. We'll talk about how O2 and CO2 are transported in the blood, and we will explain the effects of blood gases and pH on respiratory rhythm. So this is really the cool part, but fair warning, it does involve some chemistry. So if that gave you nightmares in 121, prepare yourselves. Okay, so remember that partial pressure refers to the separate contribution of each gas to the total pressure of a mixed gas. So if I have a volume of gas that's 1 liter and it's 70% oxygen and 20% carbon dioxide, the partial pressure of oxygen in that liter of gas is higher. So a partial pressure gradient is when there are differences between gas pressures at different points. So gas moves from high partial pressure to low partial pressure, and that is just simple diffusion. So let's exit this program for just a minute, and I'll draw some things out for you using Autodesk. All right, so here we have Autodesk. Let's make that full screen, and I'm going to make some shapes. So here I'm going to make a square, and here I'm going to make another square, and here I'm going to make yet another square. So we're going to say that, let me go get a pen here. Each of these has a volume of, oops, undo. Sorry, I'm still getting the hold of this. I need to select line. There we go. So each of these has a volume of 1 liter. 1 liter and 1 liter. Perfect. So now I'm going to draw in there different colors representing different gases. So I'm going to pick red equals O2, and this nice blue equals CO2. And I'm going to make different partial pressures of gas in each of these. So let's say, for the sake of argument, that in this box we have 1, 2, 3, 4, 5, 6, 7 oxygens. In this one we have 3, and in this one we have 5. Now going over to carbon dioxide, we have 1, 2, 3, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7. All right, so going back over here, I'm going to pick black. So we know that the total volume of gas in each of these containers is identical, that contain different relative amounts of mixed gas, both oxygen and carbon dioxide. So PCO2 of this one equals 3. PCO2 of this one equals 5. And PCO2 of this one equals 7. So same thing for oxygen. PO2 equals 7. PO2 equals 5. And PO2 equals 3. So if I put down here P sub tot, which is my total pressure, you'll find that in all cases it adds up to 10. So the volume is constant. The total pressure, which is how hard these gas molecules are pushing on the container, is constant. What isn't constant is the relative amounts of gas particles. So that's what partial pressure means. Now, getting back to partial pressure gradient, I'm going to get my eraser and just erase my whiteboard, and then I'm going to draw you another container where now I have a membrane, and gas is going to diffuse across the membrane. Maybe I'm just going to make a big white square. Nope. Okay. Perfect. All right. So now I'm going to select a square, and I'm going to select black, and I'm going to make a really big one. And then I'm going to draw a line down the middle. And I'm going to tell you that this line is permeable to certain gases. So if I go back to here and get this little guy. Okay, so again, red equals oxygen, blue equals carbon dioxide. So we're going to do the same dot scheme over here. So I'm going to put 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3 over here. So based on what we know about diffusion, we would expect oxygen, our little red dots, to flow from an area of high concentration to an area of low concentration until there are an equal number on each side. So that would mean that 1, 2 dots let me erase 2 over here, would flow over here. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So now oxygen has reached its equilibrium. While that's happening, oops, undo, I want blue. Carbon dioxides are going to move down their gradient. So they are more numerous over here and less numerous over here. So these are going to diffuse across the barrier until they reach their equilibrium. So I'm going to add 2 of these guys, which are going to come from over here. And now you can see we have 1, 2, 3, 4, 5 oxygen, 1, 2, 3, 4, 5 oxygen on each side, and the same is true of carbon dioxide. So the gases have diffused across the membrane in different directions. So both this way and this way, such that both gases have independently reached their own equilibrium, and the total amount of gas is the same on each side as well. So if we count our total gas particles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's how gas diffusion with mixed gases with differing partial pressures across a membrane works. So we're going to look at what just happened in this drawing at the level of the cell. So let's go back to the PowerPoint. And back we are. Okay, so that's what we mean by partial pressure gradients. Now, let's look deeper at this. The air you breathe in, and I'm going to go down here and I'm going to get my arrow. So, the air that we breathe in has about a partial pressure of 159, so close to 160 millimeters of mercury in it. And millimeters of mercury is just how hard the atmospheric gas pushes on a column of mercury to get it to go up a tube. So that's what that means. It's just a way to measure gas pressure. Meanwhile, the partial pressure of CO2 in atmospheric air is only about 0.3 millimeters of mercury, so quite a bit lower. By the time the air gets to the alveoli, we've got a PO2 of about 104 millimeters of mercury, and PCO2 is much higher at 40 millimeters of mercury. That's because at the alveolus, CO2 is actively diffusing from the blood into the alveolar air. So you're dumping CO2 into the air. Oxygenated blood has a PO2 of about 95 and a PCO2 also of about 40. Once you get down here to the tissue fluid, PO2 drops to 40 millimeters of mercury because presumably the cells in this tissue are metabolically active and are therefore sucking up via diffusion whatever oxygen is available. And they have a waste product, which is CO2, and they're going to dump the waste CO2 into the blood in the amount of about 6 additional millimeters of mercury. So by the time venous blood returns to the heart, the PO2 is about 40 millimeters of mercury and the PCO2 is about 46. So compare that with inspired air and alveolar air. These two numbers are much closer. Also notice the magnitude of change in the PO2 varies pretty greatly. So we go from 104 all the way down to 40, whereas the magnitude of change for PCO2 is relatively small, so we get a 6 millimeter of mercury difference. And there's a reason for that, and it has to do with blood chemistry. We also need to address how gas is transported in this system. So yes, we know it's in the blood, but how is it in the blood? What carries it? Is it carried at all? Is it simply dissolved? We haven't addressed this yet. So with regard to oxygen transport, 98.5% of it is bound to hemoglobin, which is a globular molecule that carries oxygen. About 1.5% of it is dissolved in the plasma. Carbon dioxide follows a different scheme. So 70% is dissolved in the blood as bicarbonate. 23% is bound to hemoglobin. Yes, hemoglobin can transport both oxygen and carbon dioxide at the same time. And about 7% is dissolved in the plasma. So let's look at some gas transport stuff. So oxygen diffuses into the blood from the alveoli, and about 98.5% of it enters the erythrocytes, which remember are red blood cells. So the reason they appear red is because oxygen bound to hemoglobin reflects red light. So that's why your blood is red. Not all critters have red blood. Horseshoe crabs, for example, have blue blood. So different pigments, different colors. So the O2 very literally binds iron in the heme group, and the iron is, give me my pen here. So this iron is Fe2+, which equals ferrous. Let's make that O a little better. Iron. And oxygen binding to ferrous iron creates the red color, and it's also the reason that blood smells the way it does, so slightly metallic, kind of like pennies. In the environment, when Fe2 plus combines with oxygen, we call that rust. So Fe2 plus O2, oxidized iron equals rust. So there's a reason that your blood tastes and smells similar to a oxidized metal, because it very literally is. So each oxygen can carry 4 O2 because it contains 4 heme groups, or excuse me, each hemoglobin can carry 4 O2 because it contains 4 heme groups. The rest is transported as dissolved gas. So what we have over here is hemoglobin, here represented as a red ball, and it's inside of the red blood cell. You don't want it out here. Free hemoglobin is bad for you. It has to stay inside your cell. So the hemoglobin binds to oxygen and to carbon dioxide. So I mentioned earlier that it can carry both, and that is true. This picture over here, we're getting into a little bit of pathophysiology. So carbon monoxide is CO, just one. And turns out the binding affinity of carbon monoxide, binding affinity means once it binds to something, how tightly does it bind and how long does it stay there? Carbon monoxide has a higher binding affinity for hemoglobin than either oxygen or carbon dioxide. So it will effectively kick these other gases off of the hemoglobin and bind virtually irreversibly to hemoglobin. So that means you can breathe as much as you want, you can ventilate your lungs all day, but the oxygen that you are inhaling isn't sticking to the hemoglobin that you have because carbon monoxide is instead. So why would you worry about this? Well, carbon monoxide can accumulate in homes. Especially if there's problems with the furnace or heating system. And it can also accumulate in cars, so car exhaust has a lot of carbon monoxide. If there is a fire in your home, there's a lot of carbon monoxide, and that can lead to smoke inhalation injury, so fire. And finally, speaking of fire, in old-timey homes, before electricity was widely available, kerosene lamps were used to light the interiors of homes, and coal was burned to heat the interiors of homes, and both of these things dump out large amounts of carbon monoxide. So in the winter, when homes were shut tightly up against the cold, not a lot of air exchange moving around in the house, and so the carbon monoxide from these lamps and from this coal tended to build up in the atmosphere. So constant low-level exposure to carbon monoxide can cause audio and visual hallucinations. So it's thought that a lot of famous hauntings were really a result of the families experiencing carbon monoxide poisoning. I'm talking about old hauntings on the order of Winchester Mystery House and such. So, carbon monoxide can be fatal because it prevents hemoglobin from binding to oxygen. It is very bad. Now, here is this picture which I will walk you through. I'm also going to make a separate video where I draw all this out. So, the mechanisms of CO2 transport, and note that we are getting our CO2 not from the atmosphere, but by creating it ourselves. So, respiring tissue is tissue that is actively making ATP, so let's go write that down. So, burning O2 to make ATP. And it's also burning glucose. So, 7% of this goes straight into the plasma in the form of dissolved gases. 23-ish% binds to hemoglobin. So here is HbCO2, meaning carbon dioxide bound to hemoglobin. And a little bit of it results in this weird compound where CO2 binds to plasma proteins, so the proteins that are present in plasma that can carry stuff, things like albumin and what have you. So we call these carbamino compounds. Most of the CO2 that is entering the cell from the respiring tissue undergoes a chemical reaction that is facilitated by this particular enzyme, carbonic anhydrase. So you can see that labeled here, carbonic anhydrase. So when CO2 enters the red blood cell, it combines with water according to the following reaction. CO2 plus H2O, catalyzed by carbonic anhydrase, makes H2CO3, which is carbonic acid. So carbonic acid is a weak acid, and it dissociates because we know acids dissociate in solution. It dissociates into bicarbonate, a weak base, and a proton, which we know is a unit of acidity. So weak base. So a combination of a weak acid and its weak base is a buffer system. So because you have both of these things in equilibrium in your blood, you can resist large changes in blood pH. But in order for this bicarbonate to be useful, it has to leave the cell. So it doesn't do you any good inside of the red blood cells. If it's going to combat blood acidity, which typically takes place in the plasma, you're going to need it to be out here somewhere. But you don't want to have a continual loss of negative charge because bicarbonate is an anion. You don't want this cell to be constantly losing negative charge because that would disrupt its membrane potential. So a process called the chloride shift happens where bicarbonate is kicked out in exchange for a chloride anion coming in. So this keeps the charge inside of the cell the same, even though every time a bicarbonate is made by this process, it gets kicked out. So it keeps the charge on the level. So this is called the chloride shift because it's a shift of chloride from the outside of the cell to the inside. It's also named after its discoverer. So you will sometimes see it called the hamburger shift, which I think is pretty funny because it has to do with hamburgers. So once the bicarbonate is gone, now we have a lonely proton. So H plus by itself is just a proton. However, this is where this reaction is linked to this one down here. So we have in this cell hemoglobin bound to oxygen. Now this begs the question, if hemoglobin has been hanging on to this oxygen since the lungs, not giving it up to other processes, how do you convince it to give up the oxygen once it gets to the respiring tissue? Well, turns out the binding affinity for hemoglobin is reduced in the presence of acids. So you can come over here, put this proton next to this oxyhemoglobin, and that will convince the hemoglobin to let go of the oxygen and exchange it for the proton. So now we have deoxyhemoglobin and a free O2 molecule that can now diffuse into the respiring tissue. So you need the carbonic acid reaction and you need the chloride shift in order to free up this proton to keep oxygen unloading. So CO2 loading and oxygen unloading are linked processes. So some other things to consider when you're thinking about oxygen unloading. Besides this, HbO2, so oxyhemoglobin arrives at systemic capillaries 97% saturated and it leaves 75% saturated, which means that you are not 100% efficient at unloading oxygen, even though this reaction is very sophisticated and good at its job. Venous reserve is oxygen remaining in the blood after it passes through the capillary beds. And that's good for you because it means you have a spare store of oxygen circulating in your venous blood just in case there's some interruption in your arterial blood. So if you've ever wondered why holding your breath for a long time doesn't immediately kill you, part of the reason for that is venous reserve. So your heart's just pumping the blood that it has. You are not sending that blood to the lungs to pick up oxygen because you're not using that. You're just sending the blood to the lungs and back for no reason. But there is still leftover oxygen in your venous blood, so you can use that, which is why you don't immediately croak if you hold your breath. So venous reserve is important. Okay, so that was stuff that happens at the respiring tissue, but we also have to consider things that occur at the lungs. I think you'll find that this picture looks really, really similar to the reactions that occur at the lungs, and that's because, as it says up here, they are simply the reverse. So if you go back a couple slides, here is what happens at respiring tissue, CO2 moving into the red blood cell, O2 moving out. Now we have an arrow reversal. And we have a reverse chloride shift as well. So as hemoglobin loads O2, its affinity for protons decreases, which frees up these protons to go recombine with bicarbonate that's coming back in, forming carbonic acid. Carbonic anhydrase is capable of facilitating this reaction in either direction, and it just depends on the relative amount of reactants and products or vice versa. So, if you have a lot of carbonic acid, it will facilitate the opposite reaction, breaking the carbonic acid into water and carbon dioxide. And then 70% of carbon dioxide leaves your red blood cells and enters the alveolar air that way. So to link this to the respiratory system, which we will be coming up on shortly, if you've ever been working out and you've wondered, well, I've been working out and losing weight and losing fat, but golly, where is all that stuff going? Well, the CO2 that you loaded at a respiring tissue is a waste product from burning glucose. So it's a leftover of a glucose molecule or fatty acid molecule that you turned into glucose after you burn it. That kicks around in your blood for a little while in the form of this stuff. And then you breathe that same CO2 out as you exhale. So if you've wondered where the fat goes, well, you changed the fat into glucose, you burned it to do work. It lived in your blood for a little while in the form of carbon dioxide, and then you breathed what was left of it out. So when you work out to burn fat, you are releasing it into the air. Pretty impressive, I think. Okay, so we know that the blood buffer system comes from carbon dioxide's contribution to the blood and its chemistry. So that gives us some information about how breath rate, so deep breathing and how fast you're breathing, affects blood pH. So acidosis is a blood pH of less than 7.35. And your body responds to acidosis by increasing breathing rate and depth. So if you have too much acid in your blood, you're going to try and eliminate CO2 from your body to get rid of carbonic acid. So that sucks up protons, which are units of acidity, and raises pH. So you can think of increases in breath rate due to acidosis as trying to scrub protons from your blood. Now, when would we see this clinically? Well, in untreated diabetes, the patients end up with ketoacidosis due to burning fats and proteins and generating ketone bodies in the blood, which are acidic. So one clinical sign of diabetes that is advanced and untreated is patients coming with very, very deep and very, very increased rate breathing, so panting, so to speak. Now, most people who present with this symptom aren't adults, but rather children whose parents didn't realize they had diabetes until they started peeing a lot, being constantly thirsty, and panting due to acidosis. It also corresponds with weight loss. So most people who end up with this are not adults, they're children, so you don't have to worry about this too much. Alkalosis is a blood pH that is greater than 7.45. So in this case, your body is going to do the opposite thing. So it's going to decrease your breath rate and depth, which allows CO2 to accumulate in the body, and that shifts this reaction the other way so that you get a buildup of protons in the blood. So it increases protons, and that pushes the pH back down to normal. So on the exam, I could give you an example of a question where I say, I put you in a room with a very, very high partial pressure of CO2, and I lock you in there. What is going to happen to your blood? And you would need to think about this blood chemistry and tell me the answer. So that concludes the respiratory system PowerPoint. In the next slideshow screencast, I will start with you the digestive system PowerPoint.